In this video, we're going to learn how to classify even and odd functions algebraically. But first of all, what are even and odd functions? Let's write down some definitions. First of all, a function is even if its graph remains the same when reflected across the y-axis. Let's also give a definition for odd. A function is odd if its graph remains the same when rotated 180 degrees about the origin. So now, using these definitions, we want to classify the functions graphed below as even, odd, or neither. Taking a look at this first function on the right, this is just a line passing through the origin. To test if the function is even, we need to see if the graph remains the same when reflected across the y-axis. So why don't we just go ahead and pick a point on this function? How about that point right there, 1, 2, and let's reflect that across the y-axis. That goes over here. And that's a problem because when we reflect this over the y-axis, we get a new point that's not on the function. So we know right away that the graph will change when we reflect it across the y-axis, so therefore the function can't be even. But let's check if the function is odd. So for this function, does the graph remain the same when rotated 180 degrees about the origin? Well, let's do this again with that one point, 1, 2. Let's rotate that 180 degrees about the origin, and that flips down to here. -1, -2, and that is indeed on the function, so that's good. Maybe let's take another point, 2, 4. That point rotated 180 degrees about the origin. It goes to -2, -4, and that is also on the function. Actually, if we take this entire bit of the function on the positive x-axis and we rotate it 180 degrees about the origin, that'll just land on this bit of the function that's along the negative x-axis. Likewise, if we take that bit along the negative x-axis and rotate it 180 degrees about the origin, we land on the bit that's on the positive x-axis. So really, the function just falls back on itself after the rotation and nothing changes. So yeah, the function is odd. Okay, so how about this function here, this parabola? Is it even? Well, does its graph remain the same when reflected across the y-axis? Why don't we take a point here? Let's take the point 1, 1 and reflect that across the y-axis. So that goes to the point -1, 1, which is indeed on the graph. How about let's take the point 2, 4 and reflect that across the y-axis? That goes to -2, 4, which is right here, which is also on the graph. So yeah, the graph is symmetric about the y-axis. When we reflect it, the side along the positive x-axis will fall on the side along the negative x-axis and vice versa, so the function won't change at all. So yeah, this function is even. And just to be sure it's not odd, let's actually check that as well. We just need to see if the function stays the same after rotation of 180 degrees about the origin. We can take that point 1, 1 and rotate that 180 degrees about the origin. That falls on this point right here, -1, -1, but that's not even on the function. So the graph would change and therefore the function could not be odd because its graph changes. Okay, so how about this function here? It's another parabola, but it's shifted right and down a little bit. Is it even? Well, let's take a test point. How about this point 1, -1? If we reflect that across the y-axis, does it lie on the function still? No, it goes over here to -1, -1, and that is off of the function. So no, the graph becomes different when reflected across the y-axis, so the function can't be even. Is it odd though? Well, does its graph remain the same when rotated 180 degrees about the origin? Why don't we take another test point for that? Why don't we actually take this point up here, that's 3, 4. And let's rotate that 180 degrees about the origin. That goes all the way down here to -3, -4, but that's not on the graph either. So the graph changes when rotated 180 degrees about the origin, so the function isn't odd either. So it's neither even nor odd. Okay, so how about this function here? Even, odd, neither? Well, let's test if it's even. Let's take a test point, how about this one here, and reflect that across the y-axis, see if it still lies on the function. So this point, it's at 3, -4 right now, and that goes to -3, -4, which is right here, but that's not on the function. So nope, it's not even. But is it odd? Let's try rotating that point 180 degrees about the origin, and that goes to -3, 4, which is right up here. So yeah, that's still on the function. What about the point here, 2, 1? If we rotate that 180 degrees about the origin, that goes to -2, -1, which is still on the function. Yeah, so it looks like it's odd. This bit here, when rotated about the origin, will turn into that bit there, and this bit here, when rotated about the origin, will turn into that bit there. And vice versa, these bits will turn into those bits. So yeah, the function is odd. Last one, what do we think about this function here? That looks a little complicated, but remember we just need to check graphically, is it the same when reflected across the y-axis or when rotated about the origin by 180 degrees? Well, let's check about reflection across the y-axis. So how about we just take a point here, 1, 3, right up here, and let's reflect that across the y-axis. We get to this point, -1, 3, and yeah, that's still on the function. Maybe we'll take the point 2, 0 right here, reflect that across the y-axis, -2, 0. That is also still on the function. So yeah, it's looking pretty even to me. You can kind of see visually that this hump here, when reflected across the y-axis, will just turn into that hump there, and vice versa. So yeah, that works out. The function is even. We can also verify that it's not odd. Say we take this point here, 1, 3. If we were to rotate that 180 degrees about the origin, we'd go to -1, -3, which is not a point on the function. So nope, not odd. Alright, next up, let's get some algebraic definitions for even and odd. These will be useful in case we don't know what a function's graph looks like. Maybe we're just given the values of the functions in these tables. So here's the definition of an even function. A function f is even if f of -x equals f of x for all x in the domain of f. Likewise, a function f is odd if f of -x equals -f of x for all x in the domain of f. Now, to use these definitions to classify the functions in the tables below as even, odd, or neither, all we have to do is plug in the negative values of f and see if the output stays the same or becomes negative as compared to the positive values of f. One catch, though, for odd functions is note that this rule implies f of 0 equals -f of 0 when x is 0 here in this rule, just subbing that in, which really means that f of 0 has to equal 0. So let's go ahead and start classifying functions. This function over here, f, is that even, odd, or neither? Well, let's just go ahead and apply the definitions. Let's take f of -x. How about f of -2? And that's equal to 3, looking in the table there. And how does that relate to f of 2? F of 2 is also 3, so f of -2 is equal to f of 2. And it looks like this is suggesting the function should be even, because the negative and positive inputs both have the same value. Why don't we go ahead and check this a little bit more? Let's check f of -1. F of -1 is equal to 7. And how does that compare to f of 1? Well, f of 1 is also 7, so f of -1 is equal to f of 1, which again suggests the function is even. It's easy to check this for 0 also. F of 0 is equal to f of 0, of course, that's obvious. Just plugging in 0 here, negative of 0 is 0, so that's got to be true. So in all cases, for all x in the domain of f, the function is shown to be even. So therefore, the function is even. Okay, so why don't we go ahead and do a similar thing for g of t to determine whether that function is even, odd, or neither. Let's take g of negative 10, that rightmost input there. G of negative 10 is equal to negative 8, which is equal to, well, how does that compare to g of 10? G of 10 is positive 8, and negative 8 then is negative of g of 10. So that means g of negative 10 is negative of g of 10. When we switch the sign of the input, the sign of the output changes as well. And that's looking like the function is odd. We've got that negative sign outside of the function there. Okay, so why don't we test this on the other value? G of negative 5 is equal to negative 3. And how does that compare to g of 5? Well, g of 5 is 3, so this is negative of g of 5. So again, when we switch the sign of the input, the sign of the output changes as well. We've got that negative sign in front of the function here. So that's again looking like the function is odd. And lastly, we have to check that f of 0 is indeed 0. Let's try that. So f of 0 is equal to, looking in our table, f of 0 is 0. Yeah. So in all cases, the function is demonstrated to be odd. So therefore, the function itself is odd. All right, last function, h of x. Let's see if this function is even, odd, or neither. Let's again plug in the most negative input. So h of negative 4, that's equal to 3. And how does that relate to h of positive 4? Well, h of positive 4 is 15. So this is definitely not equal to h of positive 4. So the function can't be even. And it's also not equal to negative h of positive 4, because that would be negative 15. So the function is not odd either. So it's neither even nor odd. Now let's classify each of the functions given below as even, odd, or neither. This time we're given functions as expressions of the inputs x. But again, the procedure is very similar. We just take negative x as the input and see how that relates to the function when given input positive x. So for this function here, f of x equals 2x, we have that f of negative x is equal to 2 times negative x. Just stick in negative x where x was. And 2 times negative x, that's equal to negative 2x, which is equal to negative f of x, because f of x is just 2x. So when we change the sign of the input, the sign of the output changes as well. That's an odd function. So there we go. F is odd. Alright, so how about g of x? Let's do the same thing. Take g of negative x. Just plug in that negative x where x is in the function. So 5 times negative x plus 1. 5 times negative x is just negative 5x, and then we've got our plus 1. Okay, so that's definitely not equal to g of x, because we've introduced a negative sign. Can we factor out the negative and show that this is equal to negative of g of x? Is that true? Well, let's try it. If we factor out the negative, we get 5x, and then switch the sign on this plus 1 to get minus 1. And 5x minus 1, well, that's not g of x. So that's not equal to g of x, nor negative g of x. So that means it's neither even nor odd. Alright, so how about this function h of x equals 3x squared? Again, just plug in negative x into the function. So h of negative x is equal to 3 times negative x squared, which is equal to 3 times, what is negative x squared? Well, squaring gets rid of the negative, so then we just have x squared, 3x squared. And hey, that's exactly h of x. So h of negative x is equal to h of x, meaning that the function is even. So now we know how to classify even and odd functions not only graphically but also algebraically. In the future, we'll continue to learn more about functions, such as how to classify their behavior at a point.